Hello everyone, welcome to today's webinar, IoT Design Space Challenges, Simulating the Power Consumption and Timing. My name is Ranjit, Application Engineer at Mirabilis Design. The major reason for taking up this webinar is the kind of challenges that the designers and architects are facing today, either in terms of selecting the hardware architectural components, or it could be optimizing power consumption to achieve better battery efficiency, or in terms of designing a network topology that helps in meeting both performance and power requirements. So before getting started with today's webinar, I would like to go over a few logistics. And here you have a chat window on your right-hand side of your desktop. And please post in your questions in the chat window, and we have people in standby, and they'll be answering all your questions. And also, I will be taking up these questions at the end of this presentation as well. So here's a quick outline about today's webinar, and I'll be talking about the kind of challenges that IoT system poses and how exactly these challenges can be addressed. And as part of it, I'll be talking about how hardware architecture exploration and workload analysis will actually help in making the IoT system architecture better. Workload analysis itself is a huge topic, and I'll be talking about a piece of it today. I'll be showing you some scenarios and example case studies as well. And in terms of energy harvesting and power management or battery efficiency itself, I'll be talking about how the kind of facilities that we provide and how exactly you can utilize these modeling technologies to be able to explore your architecture early in the design phase, to be able to conduct both power and performance analysis at the same time, even if you don't have the detailed information about your architecture or regarding your applications itself. And again, I'll be talking about the cognitive radio or the network requirements and wireless channel impacts and things like that. I'll be showing you some scenarios in terms of how exactly an adding or removing a network node will actually impact on the total system performance as well. And as a whole, I'll be showing you a lot of demo examples to give you a feel about how exactly a modeling and simulation solution will actually help you in getting your system architecture right, all the way from your semiconductors to your network as a full system itself. So here's a quick outline about Mirabilis Design for those of you who has not heard about Mirabilis Design. We're a Silicon Valley-based systems engineering company, and we provide software solutions for architecture exploration, power, and performance analysis. And the company was founded in 2003, and we are based out of Sunnyvale, California. And we have offices in California, China, Japan, Czech Republic, and India as well. We have more than 50 plus customers worldwide, and the customer profiles are actually quite different in the sense that we have customers all the way from the semiconductors companies to consumer electronics, avionics, automotive, and high-performance computing systems. And the environment that we provide is called VisualSim Architect, which is a completely graphical and hierarchical modeling and simulation environment. And I'll be using this particular tool to show you the demo examples as well in this webinar. So looking at the IoT system design challenges, we can actually broadly classify this into 4 sections. And I'm actually ignoring the concepts of your internet protocol securities and all those things, but I'm actually focusing more on the hardware architectural level and getting your network topology and things like that. And first, a selection of hardware architecture elements itself is a huge task, and most of the times this will be actually done based on the experience or some guesswork. You'll be selecting the sensors or the memory controlling units or memories, unlock front end and hardware accelerators and things like that. And it'll be actually very easy to identify based on the cost or reliability front or in terms of power factors. But when we actually look at these different characteristics at the same page, you'll actually have to consider the impact of power as well as the performance as well. The kind of trade-off studies that you need to conduct in terms of achieving a better performance without compromising on the power consumption is a huge task, and we will be actually addressing those issues as well. And in terms of the software task scheduling, as you know that you can't really afford having a large processing units or multi-core or multi-processing units in a small piece of IoT devices if it is a small piece. So you'll actually have to execute, or you'll have to map your applications in a such way that there is a kind of reduced resource contentions, and also you need to schedule your software task in such a way that the kind of interrupts that are coming in are not really impacting this end-to-end latency of a particular task that you are running on that particular small piece of your memory controller unit itself. And also we help in there to be able to understand the best scheduling algorithm, and also the kind of processing unit that you need to have to be able to meet your performance requirements as well, at the same time considering power requirements. Thirdly, we consider the network infrastructure, whether it is a wireless or wired network. So in here, we actually help in understanding how many nodes that you need to have, or what is going to be the distance between different nodes, and what is the bandwidth that you need to allocate to a particular link in your platform itself. And this is actually true for both wired and wireless network topologies. And we actually help you in getting those details correct. And on the scalability front, for example, right now you might be having 20 different nodes on your platform, but after 5 months or after 6 months, you may actually have a requirement of having 50 more or 100 more nodes into your system itself. So you need to understand whether the network topology, what you have selected, or the kind of data center that it is talking to, is having enough bandwidth to support that many nodes or that many devices that you're going to connect to that particular system itself or not. So by looking at this, I'm actually trying to I'm actually trying to go over a full system level IoT exploration itself, all the way from the semiconductors to full network plus data center processing units as well. Okay, so to address all those problems, what I just talked about, we have actually assembled a VisualSim architect in such a way that you can quickly construct those simulation models graphically and hierarchically. And the libraries are provided either in terms of stochastic and cycle accurate levels based on the details that you have with you. And these libraries are embedded with both power and timing information, which means if you construct a simulation model, the same model can be utilized for both power analysis as well as performance analysis at the same time. And these libraries are actually used to assemble your hardware architectures or network or traffic itself, or the workloads and use cases and things like that as well. And if you have any if you have any modules defined in C, C++, MATLAB, or Simulink, you can actually integrate, or you can bring those models right into VisualSim, and you can start using those immediately as well. And the analysis side that VisualSim helps you in understanding, you can actually run varieties of simulation runs to conduct explorations on selecting a particular component, whether it is a processor or memory or things like that. And also the exploration you'll be conducting to make sure that the latency on your system platform, whether it is a task processing latency or an end-to-end latency, or it could be a network latency and things like that, or it could be utilization of the resources that you have in your platform itself. You will be actually understanding these values upfront before going for an implementation as well. To just remind you, if you come across any questions, please post in your questions in the chat window. And we have people in standby, or I'll be taking up those questions in between, or maybe once the presentation is over. So looking at the hardware architectural problems that I just talked about, So mainly we are actually trying to address the problems such as how do I select, or what is the rate at which I need to run my devices, and what are the devices that I need to use in my platform to be able to meet my performance or power requirements. What is going to be the memory size that goes with my system platform itself. You're not providing too much memory itself, in which you actually may compromise on the size of your platform, or that may consume a lot of power consumption and things like that. You need to make sure that you're not over engineering, or you're not under engineering system, so you can actually get an optimized system architecture by running varieties of simulation runs. And also we help in selecting the arbitration algorithms, whether it could be based on the priority basis, or whether it could be based on the availability of the resources on the source or destination side and things like that. And on the application side, we actually help in understanding how you can map your applications between your custom ASIC boards or a processor and a FPGA itself. Consider if you're working with an industrial IoT system platform, you may actually have a combination of processor plus FPGAs and things like that. So in which it is actually highly essential to be able to understand how the software applications needs to be executed on a combination of these different set of execution units as well, to be able to achieve better performance as well as power. So once your simulation model is constructed, so we actually provide a framework in which you actually run varieties of simulations by changing the workload. For example, what happens if the rate, or if the sensor starts sending traffic for every 1 microseconds, or something like that, and instead of 10 microseconds, what is the impact of that particular traffic on the total system performance, or in terms of power consumption of the total system platform itself. You can actually inject the faults into a system and try to explore the kind of scalability of your hardware platform itself to be able to meet the requirements in terms of cost or reliability or power or performance and things like that. So at this point, I would like to go over to VisualSim to give you a feel about how exactly the models will look like, and how exactly the hardware architectural components can be instantiated as a library or a system component. And let me go over. I hope you can see my screen right now. And here we have one IoT system model in which I have 5 different devices connected across 5 different nodes, and these devices can actually connect to any of these particular hubs that I have connected over here. And that could be the selection of these nodes could be based on how far these devices are connected, or based on the bandwidth availability itself. And also I have kind of routers in between as well. And on the other side, I have an edge router, which is actually connected to a processing unit on the other side. But if I go over to these green blocks on the left-hand side over here, what I have here is, this is a hierarchical block. And if I go inside these blocks, what I have here is I have modeled the kind of devices, or instantiated the devices that models my IoT model itself. For example, I have the sensor. In this case, I have just one, but you can actually have as many sensors as you want in this module. And you have your analog front end, and you have your memory controller unit, and you have your Bluetooth core and the radio transceiver module itself. So if I go inside this particular microcontroller unit, what I have over here is I have a detailed processor module. This is actually going to be a chip inside your IoT platform itself, in which I have the processor, and I have my bus architecture itself, and I have my memory. In this case, I have just one memory, but you can actually have other 8 memories based on your requirements on the kind of devices that you're selecting. So if by looking at this particular processor block, what we have here is we actually have, we provide a set of parameters so that you can actually configure these modules or these libraries based on your requirements for every simulation run. For example, in this case, I have actually provided a parameter for my processor speed here. So initially, I'm actually running this particular processor at 16 megahertz. I can actually change this particular processor speed and try to see what is the impact of that particular increased processor speed on my performance as well as on the power consumption side. And also I have my cache execution units as well. For example, in this case, I have an L1 cache over here, and I have provided the size of my cache itself, or the kind of, if there is a cache miss, where do I go and get the data? In this case, I'm actually going and getting the data from the RAM, which is actually, again, a DDR type, or it could be any of the other types as well, whether it could be SDR type or DDR, DDR2 as well. And also we support other memory technologies such as low power DDR technologies as well. And these complete parameters are completely configurable. So based on your memory that you're selecting, you can actually configure these parameters as well. So going back to the model, or going back to the top level, what I'm going to do is I'm going to run this particular model, and before running the model, I'll just go over a few items what I have here. So I have my devices connected across, and each devices are having processing units and memories, and these are a network node or hubs that we have. And on the network management side, we have the routing table over here. What it does is it actually allows you to define the connectivity between different nodes on the platform. For example, you have your source node and destination node, or this is an intermediate router, and what is the distance? In this case, this is actually 10 meters, and I have provided what is the bandwidth that I have provided for that particular link itself. You can vary these parameters based on your requirements. And on the routing algorithm, what I have over here is I have by default I have Dijkstra routing algorithm, but you can actually use your own user algorithms as well. And based on that, these network architecture will actually work in that particular space. And the power table that I have on the left-hand side over here, what it really has is it has a list of components that I have in my hardware architecture. Well, it includes my processor, bus, memories, and the low power Bluetooth modules and things like that. And for each devices that I have provided power details. For example, in standby state, what is the power consumption of that particular component, or what is the power consumption in active state, or wait state, or idle state, and things like that. So what it really happens is when you run the simulation, it will keep on monitoring the activity of these particular devices or state of the devices, and it will actually update the power consumption. That actually allows us to capture both instantaneous as well as average power consumption of the system platform itself. So on running the simulation model, so the reports can be generated to address the kind of questions that you may have. For example, in this case, I'm actually looking at the network latency, including latency of the network and also the data center latency itself. So in this case, what I'm doing is I'm actually capturing the end-to-end latency between one node to another. So I have listed different nodes that I have here. I have 5 different nodes, and this is actually my latency graph that I have captured over here. And here on the top left corner, what I have over here is instantaneous and average power consumption of my platform itself. So in this case, you can actually see that my average power consumption is very less, but there are some times in which you can actually see a kind of spikes here, which is actually, you can correlate with the network latency as well, in which you have a lot of activities that are going on, and the system power consumption is quite high at those particular timestamps. And these power spikes could actually impact on the total system performance as well. So it will be actually helpful on getting these information upfront as well. Also, I'm looking at the Bluetooth activity as well. In this case, I'm looking at when exactly you are doing your retries, or when the channel is busy, when you're actually transmitting the packets across your Bluetooth channel as well. And on the right-hand side over here, I have the kind of statistics that I have captured for my processor here. So this is my MIPS for a processor inside my device 1, and the maximum MIPS, million instructions per second, that I'm getting here is about 8.8 million instructions per second. I'm actually running my processor at 16 megahertz. I can actually change these uh, configurations by double-clicking on these devices, and I can configure it based on my requirements as well. In this case, the device is actually requesting a size of 256 bytes of data, so that is actually going across my network as well and exploring the details. So in addition to that, what I have in this particular model over here is I have at the bottom, what I have here is a capability to add or remove a link in the complete system model itself. For example, what happens if there is a link, if the link between my device 5 and edge router gets disconnected? What is the impact of that particular disconnection on the other on the performance of the other nodes itself? Or what happens if you add a link to your network, and what is the impact of that particular adding a link on the network performance as well? So what I'm going to do at this particular point is I ran the simulation just now, and in that case I was actually not using my device 5. It was actually completely disconnected using our remove link block. So what I'm going to do is I'm going to add the link back to the network at 40 milliseconds or something like that, and I'm going to again run the model to be able to see the impact of adding an additional node into my network. And I can actually see that initially up to 40 milliseconds, everything is going very fine. But after adding my network node, additional node, I can actually see that the network latency is actually quite high. But the problem is I'm actually not seeing the kind of increased latency for my device 5, but I'm actually looking at the problem of adding an additional node is actually causing increased latency for my device 2 here. So the problem is somewhere else, and device 2 is actually having a problem. If you add a additional device over here, you can actually see an increased latency over here. That tells you that there's a lot of buffering that is happening in your network itself, and the solutions that that you need to take care is, what I have done over here is I have provided a bandwidth of 10 megabytes per second, and I have told that the distance between node 5 or device 5 to my router is about 100 meters. So what I can do is I can actually increase my bandwidth allocated for that particular link, and also I can decrease the distance between that if I want to. And again, running the simulations to understand impact of changing the or link bandwidth on the total latency, I'm actually running the model again to be able to understand what is really going on. So now you can actually see that there is actually a little bit of increased latency, but it is actually quite less. And earlier it was actually nearly 40 milliseconds of network latency, but in this case now you can actually see here the peak latency is a little bit of nearly 5.1 milliseconds or something like that. So this is how you can actually explore your system considering your hardware architecture as well, and also the network in the system platform. And this actually tells you that whether adding an additional node will actually increase the latency or decrease the latency, or the kind of other problems that it may cause later in the design process as well. So I'm going to go back to the presentation now. So here's the kind of list of IoT modeling libraries that we offer. That includes the libraries all the way from the interfaces, whether it is a low-power Bluetooth module, or cognitive radio technology, and PCI or PCI Express or Rapid IOs. In terms of processors, we have processors from ARM, Intel, PowerPCs, MIPS, and all that. And most of these libraries that we provide are completely configurable, and these processor libraries that we provide are not really an kind of ISS or something like that. So these libraries are actually accurate enough to conduct architecture exploration in the early design phase. And we have seen that the accuracy of the reports that we provide are nearly 90 to 95%. In most of the cases, it is much more than that as well. And in terms of the storage technologies that we provide, we have all the way from flash memories or HBMs or low power memory devices or SDR, DDRs and SSDs and things like that. And these libraries actually um, helps in achieving your system architecture kind of quickly and accurately as well. Okay, so in terms of the analysis and reports that we have actually conducted over here, so we are actually looking at the kind of end-to-end latency, and we are looking at the task delay in the processor itself. We also look at the throughput in terms of million instructions per second or megabytes per second for a bus or a memory technology. Also, we are looking at utilization of the resources and task delays, and all these values are actually provided in minimum, maximum, mean, and standard deviation. This actually tells you the kind of if the maximum value that you have received is quite high, whereas your average value is very less, that actually tells you that standard deviation is quite high, and that particular system is really having a problem, and you may actually have to address those problems. In terms of processor-centric statistics, we actually provide execution or statistics for the execution units or registers and pipelines. And also we provide details on the flash times and stall percentages and thread swaps and context switching details as well. And also you can capture detailed pipeline activity as well. So in terms of wireless, there is a question on what is model for the wireless channel. And in the model, what I have over here is I have inside my device, what I have over here is I have a Bluetooth core in which I have my Bluetooth module that I have modeled, and the Bluetooth module actually is accurate enough to the specifications what we have provided. And in this case, I have the Bluetooth node over here, whereas the hub is actually located outside of my device itself. So that way you can actually switch between multiple multiple Bluetooth devices can actually try to link to a particular Bluetooth hub itself. So that way you can try to understand how many Bluetooth devices a particular hub can actually connect to. Okay. I hope I have answered your question. So going back to the presentation over here, so what I have here is I have the details on the power and battery exploration itself. So what we do is on completing the kind of problem or on addressing the problems in terms of selection of a component or selection of a configuration for a system platform, we look at the kind of problems in terms of battery selection itself. What is the size of the battery that you need to have, or what is going to be the efficiency of a particular battery when you are actually integrating that battery to your system itself. So what we do is here we provide details on what is the maximum current load that a particular battery is driving with, and the kind of power management statistics or the states. And also we look at the details on self-charging and discharging techniques as well. And also we look at the voltage and frequency scaling. And the kind of reports that we generate for power modeling in this particular scenario is looking at the charging and discharging cycles on the overall efficiency of a battery itself, how many times you're charging and how many times you're discharging. And also we're looking at the self-discharge capabilities or the kind of problems on the total life cycle of the battery itself, and how many devices a particular battery can offer and what is the maximum size that I need to go with. And to be able to support that, what we have here is all the library, as I mentioned earlier, all the libraries are embedded with both timing and power information, which means you actually have your functional execution in the block, and also at the same time you have a timing execution as well. For example, when you're executing a particular function, that particular function takes certain time period to service that particular function itself on a processor core, or maybe on a arbitration scheme or something like that. So that particular time will actually impact on how much time that particular device is in active state, or maybe in standby state or wait state. So that particular details of understanding in which state that particular device is, we actually compute the dynamic power consumption of that particular component itself, and then we actually compute, or we actually add that particular generated power consumption to the top level power manager that provides us the instantaneous and average power consumption. And looking at the battery performance, we look at the charging and discharge rates, or current surge, and battery aging capabilities, and charge cycles or overheads and things like that. And at this point, I would like to go over to a VisualSim model. And what I have over here is I have a model of an IoT component. In this case, I have not considered any network or something like that, but it is purely an IoT module in which you have your power generator and harvester. In this case, it is an photovoltaic cell that I have connected, and you have your power management unit, and you have your LDOs, and you have your other devices connected. For example, you have your sensors, interfaces, memory, uh, uh, microcontroller unit, or accelerator, and RF front end itself. And on top of it, I have the battery, which is actually an CR2032, which is providing 3 volts of battery. But what we do is we actually have a table in which you can actually select varieties of different types of batteries, and based on the battery that you select, the power consumption of or the kind of efficiency will also change. Also, the kind of charging and discharging rates as well. So I'm going to run this particular model. I'm actually running this particular model for a 1 year of time period, which is actually a simulated time period. So what I'm looking at in terms of the reports is I'm looking at the battery charge and discharge cycles. So in this case, we have provided a condition in which if your battery level goes to a level of 50%, then you actually charge your battery. Unless you reach your 50%, the devices will start consuming that particular battery power, which is actually available in that particular case. And I'm actually looking at the battery life over here. You can actually clearly see here there is a kind of steady slope here, which is actually based on the kind of self-discharge rate. And also there is a kind of sudden kind of decrement in the power battery life itself. This is because of your charging and discharging cycles that are happening in the module. And on the other side, what I have over here is I have the statistics on the power consumption of different devices for different activities that I am actually running on the platform. And I also have an histogram plotter, which actually provides me details on the end-to-end latency, or the application latency on my target platform itself. Here I have 4 different sequence of activities, which is actually my different tasks or application that I'm running. I'm actually looking at here, sequence 2 is actually having an highest latency in this particular module, whereas my sequence 1 is actually having my least latency in this particular module over here. And at the left-hand side over here, what I have here is I have the lifetime energy consumption of my full system itself. It is not just about a particular component, whereas in this case I'm computing full system power consumption over the time period. Okay. And we also have a detailed statistics for the power consumption, in which you actually have the details such as what is the average power consumption of your complete system, and what is your maximum power consumption of your complete system. uh, in watts, and also we provide in joules as well. And that also includes power consumption details on individual component basis as well. Okay, so this includes much more than just exploring the battery or just exploring the device power consumption. But what we have over here is we have a power or energy harvester in which you have in this case it is a solar panel. So what it really has is I have different seasons modeled, and I have for every season I have provided power profile details, for example based on hour basis. 0 to 7, 7 o'clock there is almost no power generated, but you may actually have some power generated in that particular time period. And also in this case I have between 11 a.m. to 3 p.m. you actually have a peak power consumption which is of 90% of the power generation that can be actually achieved in that particular duration. So on the use case front, what I have over here is I have different sequence of activities that I'm running here. And these sequence of activities can be sequential or these can be parallelly executing, which means you can wait for completion of a particular task, or you can keep on running all the tasks parallelly based on the resource availability. Your hardware platform will be executing that. And the sequence of activities I have provided over here, for example, you receive a trigger from your sensor and then go to your MCU and go to your accelerator and send the transaction off through your RF module itself. Similarly, you can have as many as tasks as you need as a set of use cases in your model as well. Okay, so I'm gonna go back to the model here. So I have not talked about one important aspect over here, the idea of having the power management state machine itself. For example, in this case, this I think it'll be a little bit hard to read. I'm sorry about that. It's a bit small in size. So here what I have over here is I have different states for a particular device itself. For example, when your device is in active or sleep mode, or for example you may actually receive some uh, activities through GPIO pins or something like that, that may actually push your device to wake up and pre-processing. And then on receiving a particular task, you may actually push that particular device to a low power mode, and based on the kind of activities, for example, transmission or receiver, you can actually select whatever the type of kind of cost or the kind of power overheads that you would be actually going through. For example, in this case, what I have over here is low power mode to advertisement mode, and then you actually receive the data and then go to acknowledgement. And this loop can actually go on and based on the kind of activities that are happening in the platform as well. And this particular power management state machine, what it really does is it actually helps you to capture very accurate power consumption details, and also it helps you in defining the behavior activity for your device itself. For example, when you need to push your components to a low power mode, or when you actually have to push those devices from sleep mode to wake up mode or something like that as well. Okay, so in terms of power, in terms of energy harvesting and battery libraries, what we have over here is we have different set of energy harvesters all the way from solar panels to the motor or piezoelectric or thermal and wind type. And for every power harvester modules, we actually provide different set of parameters. For example, you can define the efficiency of power generated, and you can provide details on start and stop time for the power generation. Also, you can provide the charge capacities and what is the maximum charge that a particular harvester can generate. And also, you can import the power profile if you have any power profile as a trace file as well. And in terms of the battery I just talked about, we provide a different set of batteries to be able to explore your system model. That includes your lithium ion or nickel metal hydride or nickel cadmium batteries, or it could be lead acid and things like that. Again, different batteries are provided with varieties of attributes that includes your voltage levels, current or C rate, or self-discharge values and energy densities and things like that as well. And the kind of reports that we generate for a battery level is to be able to understand the life of the battery or discharge rates and average battery power consumption and charge and discharge cycles as well. And consumption by the loads. There is actually a question. There's a question on can I import the battery data sheet by cut and pasting the image of a efficiency curve or a current curve. So what you can do is cut and paste of the image is not supported right now, but what you can do is if you have the data sheet information of that particular power curve, it could be efficiency curve, those CSV files or spreadsheets can be actually imported to VisualSim and you can start using those values as well. Okay, so here's a kind of IoT system model. In this case, I have 10 different nodes that are connected and 2 different routers and then server over here, which is actually I just showed you in a little while ago. And the purpose of showing you this particular library or the kind of model over here is to be able to or the kind of ability to scale your system. For example, you can instantiate these blocks as many times as you want. And also we have a concept of dynamic instantiation as well, in which you actually model these green blocks in our dynamic instantiation block, and you can instantiate it 100 times or thousands times, and you can actually call these those different instances will actually act as a different devices in the model as well. So in terms of scalability, we provide a lot of flexibility over here, and also each instances can actually carry its own parameters or configurations as well. And this was actually the kind of analysis that I just talked about, considering a particular IoT component itself and considering the photovoltaic cells or the harvesters into the consideration, and to be able to understand impact of charge and discharge cycles and the battery characteristics on the total efficiency that you would be getting, or understanding the power requirements or the kind of selection of a particular battery to be able to meet your requirements as well. And here's the kind of reports that we generate in terms of battery specific. For example, in this case, we are looking at power consumption of a particular battery over the time period. And also we are looking at the battery life itself. For example, you can actually see here there is a degradation of the battery life here, but suddenly there is a kind of a sudden surge has come in between, and you can see the kind of impact of that particular sudden surge on the battery life as well. And also we'll provide details on at what timestamp you have received a sudden surge on the system platform, and you can try to understand what is the impact of that particular sudden surge on the battery life or the kind of battery power itself. Okay. And in terms of the system platform, I just showed you in an example. You can provide, you can capture details on the process centric as well. What is the performance that you're getting? And you can also get the details on network latency as well. What is the impact of adding an additional node or removing a node on the total performance of a particular system? And also you can capture details on what is the kind of how exactly the messages actually passed from one node to another. For example, in this case, I'm looking at device 4 RF node is actually my source node. It actually gone through router node 1, and it is my destination is my edge router, while edge router actually has sent an acknowledgement back to my device 4 via router 2 over here. So these kind of scenarios you can actually identify and capture, and you can actually understand, or you can actually make decisions whether these scenarios can be possible in the real system, or the kind of additional problems that you may actually uh, come across because of unexpected behaviors of the system platforms as well. So I would like to, at this particular point, I would like to go over to a simulation model, and the purpose of showing you this particular model is to be able to simulate your cognitive radio technologies, or in this particular case I'm actually simulating a MANET node protocol here. In this case I have three different nodes which are actually modeled as these circles over here, and what I have here is I have a workload over here which actually keeps on generating traffic for different nodes here. In this case my source node is my node 1, whereas my destination node is my node 3. So what it does is it actually keeps on looking at which device or which node is actually close to me, and it actually hops through that particular intermediate node to reach its destination node if it is not reachable. So what I'm going to do is I'm going to run the model for this. So you can actually see the activities that are happening in the model as well. For example, at what place it has started and in which direction it is going. For example, each node can be actually provided details on in which direction you're actually going. And also you can provide details on where exactly that particular node is located. Okay. And looking at the statistics or the reports that I'm looking at, what I'm having here is I'm actually having the latency between my node 1 to node 3 here. So I can see here, initially the devices were very close, but later on the devices are getting far, and the device on node 1 actually had to go through node 2 to reach my node 3 over here, which actually added an additional latency on my network platform itself. So looking at the kind of statistics or the activities that are happening, these reports will actually help in understanding what is the distance between different nodes that are happening, and what is the kind of hop details that you would capture to be able to understand what the connectivity details between multiple nodes as well. So you can actually integrate these details into the complex IoT system platforms to be able to understand which hub is close to me, and how can I actually select a particular hub, and what is the impact of selecting a particular hub on my total system performance as well as power consumption of my system platform as well. So in addition to that, once you construct your simulation model and once you have conducted varieties of exploration, so what do we provide here is we actually provide a framework, which is, we call it as VisualSim Explorer. What it does is you can export your simulation models, including the documentation, into an HTML format, and you can save it in your central server, and you can actually share those simulation models through our tool, which is actually a tool in which you actually install your models and share your models. And these simulation models can be shared with the teams maybe located in somewhere else, or you can actually share those models with your clients or suppliers to get early feedbacks on the kind of specifications that you might have designed or collected. And these models can actually come out of the browser itself, and they don't really have to install the software, and as they can actually read through the documentation, so you don't really have to share a lot of documentations on the systems that you're constructing. Instead, you can share the simulation model along with the documentation, and they can run through the models, and they can change the parameters to be able to understand impact of a particular configuration on the system performance and things like that as well. So to conclude this particular webinar, the environment that we provide actually helps you in making the architectural decisions based on the quantitative results instead of guessworks or the kind of analysis, mathematical analysis that you would be conducting. And simulation itself will actually, or simulation models actually includes both power and timing information, which means you are actually exploring your both timing and power requirements in the same platform, which actually very beneficial at the early stages of design process when you're making design decisions. And you can actually inject faults to your system models to be able to understand the problems that you could that the system could come across once the system is deployed and things like that. You can inject all those errors upfront and try to understand what is the workaround solution that you may have, or the kind of solutions that you could get to solve those problems itself. And once your simulation model is constructed, you can actually export it as a documentation and you can share it with your teams and customers. That way you will be actually eliminating the challenges in terms of communications and things like that. So that improves the success of the project as well, and also that improves the quality of the project as well. So this concludes this particular webinar, and now the session is open for questions and answers, and please go ahead and post in your questions